Hi guys. Today we'll start with the first session of Let's Learn session. So here my main focus is on to discuss briefly how the reformer architecture looks like. Like every one of us are familiar with the transformer architectures, but since its inception 4 years ago, it has gone through lots of changes, and the focus was mostly on making the transformer architecture more efficient. So in those lines, around 1.5 years ago, this reformer architecture was introduced. And recently, there are still more advanced, efficient architectures when compared to reformer as well. Those are named as a performer, linformer, and longformer. So maybe in the upcoming sessions, I'll discuss on those as well. So coming to the agenda, today I'll just give a high-level overview of transformers, since most of us would be already knowing about this. Later, I'll discuss the inefficiency of a transformer towards longer sequences. And later, I'll introduce the reformer and discuss briefly on these four topics: axial positional encodings, chunked feed-forward layers, reversible residual layers, and locality sensitive hashing. And at last, I'll show the benchmarking results obtained for memory and latency for reformer as well as BERT during the training and inference. Yeah, so coming to the transformer, just a high-level overview. So before transformers were introduced, the recurrent neural networks and LSTMs were in place. And we know that the tokens were processed sequentially using RNNs and LSTMs. As you would remember, the timestamps that we were using in RNNs and LSTMs. So each and every token in a particular sentence was processed sequentially. And later on, even the problems of vanishing gradient, and if the document length or sequence lengths were considerably large, then the RNNs and LSTMs were facing difficulty in remembering the context. So that is where the transformer architecture was evolved from sequence to sequence models. So the transformer architecture, though even it has some limitation on the sequence length, it was able to it was able to handle long range dependencies when compared to the RNNs as well as LSTMs. If you can recall, the transformer architecture or BERT-based models, it restricts the sequence length of an input token to 512. So even there is a setback or the long range dependencies in transformer, but it was far better than what RNNs and LSTMs were able to do. And later on, the attention mechanism, which was first introduced in transformer, it gave weighted significance to each part of the input data, so that the model will be able to learn the context, specifically when it comes to any kind of language learning and downstream tasks like paraphrasing or NER, sentiment analysis, whichever it might be. So during the pre-training phase, it will be an unsupervised learning that we'll be doing for transformers. And later on, once we want to fine tune it to specific task or downstream task, we with the label data available, we'll do a supervised learning. So right side is the architecture which you will be familiar with. So this is the encoder and the decoder part, which will be for BERT small, this will be 12 layers of encoder and 12 layers of decoder. And for BERT large, it will be 24 layers each of encoder and decoder. So coming to the positional encodings and residual layers that are introduced already in transformer, this is just an introduction. So positional encodings, as you are aware, it accounts to the order of words in the input sequence. So as attention does not account to the order in which an input sequence is present. So these positional encodings will give the positional information of the the tokens in the particular sequence. So these positional encodings are important to make the sentence legible to grammar and all, along with the context importance that is taken care by the attention. So at the bottom in this image, you can see the positional encoding that has been assigned to these tokens. So there are 3 tokens in the input, and for each of these tokens, there are embeddings which are added with the positional encodings. So here you can see the first half of the positional encoding is with one color, and the second half is with another color. This is because the first half is generated using a sine function, and the second half is generated with a cosine function. And later on in the encoder part, you can see the addition and normalization layer. So here what basically it happens is, since I mentioned the bird small bird base, it is having 12 layers of encoder and 12 layers of decoder. So these are considered as pretty much a deeper neural networks. So as and when the network depth increases, there would be a problem of vanishing gradient during back propagation. So in order to preserve the gradients, we usually add these addition and normalization layers. This was actually introduced in the ResNet architecture of computer vision initially. Later on, it was also concatenated to the transformer architectures due to its success. So residual layers, they preserve the gradients during back propagation with identity functions, even though if the gradient is very small for a particular activation layer, the identity functions whose gradient will be equal to 1 would get added to the original input, so that the gradients are preserved here. So here you can see from the self attention, we are getting the vector z, which is getting added with the vector x. So x is the input, the sample input embedding. So even if the gradient dou z is very minimal, the identity function is getting added so that the gradient is preserved, and during the back propagation, everything will propagate to the initial layers as well. So coming to the inefficiency of a transformer, the first one is the positional encodings. So the positional encoding matrix needs to be loaded into the memory and stored into the disk. So it leads to memory overhead with increasing sequence lengths. So suppose if you have around 512 tokens in a particular sentence, so you are supposed to create a positional encoding matrix for all those 512 tokens with a specified hidden dimension. Suppose if the hidden dimension is around 1024. So it will be a 1024 by 512 matrix. So you can assume this much a big matrix, how much memory it would take if you consider float 32 or float 64 precision. So when you save these models, even the positional encoding matrix would get saved, and so that is stored in the disk. And whenever you are doing the inference, even these matrices would get loaded during the inference time. So this is creating a memory overhead to the systems. This is the first one. The second one is the depth of feed forward layers. So as I mentioned in the architecture, so after the self attention layers, there is a addition and normalization layer, that is the skip connections or residual layers that I mentioned before. After that, you can see the feed forward layers. There are 2 feed forward layers after the attention. So if the depth of the intermediate feed forward layer after attention is of a larger size when compared to the final feed forward layer. So while calculating the activation functions for these feed forward layers as well, if the depth of the feed forward layer is large, then it has to store the activations for these feed forward layers as well, so that the back propagation will calculate the gradients and does the updations. So this is the second inefficiency. The third one is the number of layers. As I mentioned before, there are 12 layers in bird base and 24 layers in bird large. So for all these 12 or 24 layers, the activations needs to be stored so that during the back propagation, the gradient updates will happen. So with each layer increase in the architecture, it requires a large memory that will be stored in the RAM during the back propagation. So this is the third inefficiency. And the final one is the attention computation. So since you would remember that the way the attention is computed, suppose the sequence length is 20. So for every token in the sequence, the attention matrix will get computed with each and every other token in the sequence. So if the sequence length increases, then it will be a quadratic complexity that will be assigned for attention mechanism. So here you can see the computation of attention on sequences of length L requires O of L square, both for time as well as memory. So it is taking a quadratic complexity for both time as well as memory. So this will not be feasible. So that is where due to attention which is taking O of L square, that is where the sequence lengths were restricted to 512 in transformer or bird-based architectures. Because if it was beyond 512 with whatever the infrastructure that the people will be using, the system would get crashed. So that is where 512 was chosen to be the best for transformer architectures. So coming to the reformers, so here, since I mentioned in the agenda, I'll be discussing on these four. So the first one is to so the reformer, it will be able to process up to 500,000 tokens at once. So which is right now set to 512 in transformer. It can be increased to up to 500,000 tokens. So this is a very significant increase. After that, this is possible because of these four optimizations that have been done. So the first one is the reformer's self-attention layer. I'll be discussing on this briefly in the next coming slides. So here, where is this? Yeah, at the right side, you can see the memory and time complexity associated with each of these different architectures. So since I mentioned there will be a quadratic complexity for memory as well as time, here you can see the L square term. So this is L means the sequence length. So L square memory complexity as time complexity can be observed for a transformer architecture. Whereas in reformer, you can see there is no square term. So here the optimization is such that the O of L square will get reduced to L log L, so that there is no nonlinear term in this Abigo notation. Any questions till now?
No, for me it's clear.
Okay.
Yeah, no questions for now.
Yeah. So coming to the locality sensitive hashing. This is replacing the self-attention mechanism that is being shown in transformer. So in locality sensitive hashing, what happens is the main aim is to reduce the quadratic complexity to the logarithmic time complexity. So here, instead of calculating the attention scores for every token with every other token in a particular sequence, we try to chunk it down based on the buckets that we form. So at the right side here, you can see if these are the list of points in the higher dimensional space. we try to randomly build hyperplanes. So here you can see H1, H2, and H3 are three different hyperplanes that are drawn on this higher dimensional space. So after we draw these higher hyperplanes, we do the bucketing. So here you can see after this A, B, C, D are in the same bucket. So at the last, you can see the bucketing conventions where A, B, C, D are in the same bucket. Yeah, here you can see the A, B, C, D are in same bucket. So once the bucketing is done, we just sort out all those points which are in the same bucket. So in the left side diagram at the top, you can see the bucketing. After that, we sort all the points based on the buckets in which they belong to. So all the blue buckets are together, all the yellow buckets are together. So once the bucketing is done, so some of the times it might happen that the buckets are skewed. Some buckets might include many number of data points, and some other buckets might include only few data points. So in order to make it yeah, independent of the number of data points in a particular bucket, we try to fix a chunk size and divide it based on the chunk size. So here you can see this complete sequence has been divided based on the chunk size 4. So the attention is calculated only on these 4 tokens. So here you can see the attention that is being calculated with a particular token with each other token in the same bucket. So now the time complexity is reduced a lot with from quadratic to logarithmic time complexity. Yeah. So as and when since these random hyperplanes that we draw in the higher dimensional space, so if we draw a very limited number of hyperplanes, the accuracy might be low when compared to the global attention of transformers. So this will depend on the how many number of hyperplanes or hashes we project onto the higher dimensional space. So it was observed that the hash values set to 8 was equivalent to the global attention performance achieved by transformer architecture. So I guess you remember about the approximate nearest neighbors that I was talking about for suggested communities, which was able to bring down the search latency from 4 seconds to below 100 milliseconds, right? So the same approach is being used even in the locality sensitive hashing. So here these hyperplanes are responsible in detecting the nearest neighbors, and those nearest neighbors are later used to do the bucketing and sorting. So this can be considered as approximate nearest neighbor search, which is coupled with locality sensitive hashing. So coming to the next one, that is reversible residual layers, that is RevNets. So as I talked about the ResNet architecture, which had first introduced the residual connections or skip connections. So here you can see the left diagram, which is mimicking the addition and normalization layer that I showed in the transformer architecture. So later on, RevNets were introduced, which are reversible residual layers. So this one, why is it of more importance is, since I mentioned that with the increase in the number of layers in deep learning architectures, the number of activations that gets stored in order to compute the backprop gradients would increase a lot. So that is where this RevNet architecture was introduced. So here what we do is we do not store any activations during the forward propagation, irrespective of how many number of layers we have in the architecture. It might be 12 or 24 or 48, how many ever number of layers we have. So instead, what we do is during back propagation, these reversible networks, they'll be able to recompute the forward activations, and later it on the fly, and later it will calculate the back propagation. So this will reduce a lot of memory overhead, because all the activations are getting reconstructed exactly from the subsequent layers activations. So here you can see that instead of initially we are having x1, y1, and y2. So here, in order to reconstruct the forward propagation activation, so we are having copies of the input as well as the output. So instead of having just x1, we are having x1 as well as x2. So here we are having two streams, x1 as well as x2, y1 as well as y2. So during BAP, so here you can see the flow. This is for forward propagation. X2, so here F is the attention block, and G is the feed forward block. So X2 plus here, yeah, Y1 is X1 plus F of X2, which is X1 plus F of X2, and later Y2 is X2 plus G of Y1, X2 plus G of Y1. So here you can see these two streams are getting recalculated during the backward pass. X2 is equal to Y2 minus G of Y1, and X1 is Y1 minus F of X2. Here you can see the flow. So in this way, we are not storing the activations. Instead, we reconstruct them again during the back propagation. So this will reduce the memory overhead. But since we during the backward propagation, we are again reconstructing the activations. This might increase the time complexity. So obviously, every time there will be a trade-off between the time complexity as well as the memory overhead. So here we are increasing the time complexity at the cost of reducing the memory overhead. Yeah, so in this diagram, it will be more easier to visualize. So here there are two streams, x1, x2, and y1, y2. And the G block and F block are the attention as well as the feed forward blocks that was mentioned in the previous diagram. The third one is chunked feed forward layer. So here, as I mentioned, in the transformer architecture, here it would be visible. So after the attention block, there are two feed forward layers here. So in these, so that is the continuation of this diagram. So there are two feed forward layers. One is the intermediate layer, and one is the output layer. So the size of the intermediate layer is significantly larger when compared to the size of the output layer. So here the chunked feed forward layer, what it does is instead of storing the intermediate layer matrix, we are directly computing the output with respect to the input. So here you can see that there is no dependency on each of these individual tokens. So we can process all these in parallel. So we are not storing the intermediate matrix. Instead, we compute the output matrix from Z1 with Y1 without storing it. So here as well, we are decreasing the memory consumption. So this is very useful whenever there are very few attention heads and large feed forward layers. So if the feed forward layers are of the size of 10,000 or 15,000 number of neurons in those feed forward layers, then this chunked feed forward layer technique would be very useful in decreasing the overall memory. The last one is axial positional encodings. So I guess I mentioned on this in the starting diagram. So suppose if the number of tokens are 0.5 million tokens we are dealing with, since this is a maximum limit that can be done using reformer. Suppose if we take this to the maximum extent for 0.5 million tokens, and for each of these tokens, if 1024 is the hidden dimension, then the positional embedding matrix accounts to around 2 GB. Just for if you take this as 0.5 million into 1024 matrix. So it would consume a large amount of memory, both when loading the model into the memory as well as saving it into the hard drive. We try to factorize this huge matrix into two smaller matrices using axial positional encodings. So after doing the factorization, after we get two individual matrices of relatively smaller sizes, we can see the size reduction. It was taking 2 GB for the same configuration, which was reduced to 3 MB. So this is a very significant drop in the amount of memory that was reduced. So this is significant during training as well as during inference. I'll show the benchmarks in the next slide. So here, for an example, for you to make it easy to visualize how the axial positional encodings work. Suppose you consider there are 49 tokens in a particular sequence, and each token is having 4 as the hidden dimension. So this will be about a 49 by 4 matrix, right? So here at the top, you can see there are 49 tokens. Here you can see E49 with each one having 4 as the hidden dimension. So in axial and positional encoding, what they do is they factorize this whole 49 by 4 matrix into 7 by 1 and 7 by 3. So here you can see the bottom layer has been made into separate matrix, and the top 3 vectors are made into another matrix. I'll show the visualization in the code once more. So later during the training and inference stages, the matrix for positional encodings get reconstructed with help of these two matrices, the smaller matrices. Coming to the benchmarking of memory and latency. So the axial positional encodings. So before you do the factorization, suppose for 0.5 million tokens with each of 256 hidden dimension, you can see the number of parameters. And after doing the axial positional encodings, you can see the number of parameters. So here it is 136, 136 million. And here it is just 2.3 million. And coming to the training speed, when compared to the time complexity and the memory complexity, you can see there is a significant drop. Without using the axial positional encodings, it is taking 1.7 GB during training, and with using the axial positional encodings, it is just taking 755 MB for a batch size of 8 and sequence length 512. Coming to reversible residual layers, so these are the metrics for BERT. So for BERT, 4 layers, 8 layers, and 12 layers, you can see the how much memory that is consumed for BERT when coming to the residual layers. So like this one, if you can remember, if we are storing the activations at each and every layer, you can see how much memory is being consumed with the increase in the number of layers for BERT. So coming to reformer, we are not storing any of the activations with the increase in number of layers. Instead, we try to reconstruct them using reversible layers. So here you can see for the same configuration, what is the memory that is being consumed. For BERT 12 layers, it is 9 GB, and for reformer, it is just 2.5 GB. So the importance of this architecture is if you are not having more compute resources while training the language models, it is very essential that you choose the main the most efficient architecture, so that it will fit into your compute resources and you will be able to do the fine tuning or training. So that is where the advanced versions of transformer architectures come into picture. This the next benchmarks is for chunked feed-forward layers. So here you can see the memory that is being consumed. So the initial one, it is for less number of feed-forward layers. So here there is no significant drop in the memory. So the bottom benchmarks you can see without chunking it is taking 9 GB, and with chunking it is taking 6 GB. So this is for feed-forward layers having more than 15,000 number of neurons. Coming to the final benchmark, that is locality sensitive hashing. So the reformer architectures with the global attention, these are the metrics in the first table, and the reformer architecture with locality sensitive hashing, these are the metrics at the bottom. So here you can see with the global attention, it is taking 8 GB for 8192 sequence length, whereas it is taking 4.5 GB for the same sequence length and batch size using locality sensitive hashing. So with the increase in the sequence length, you can observe the quadratic complexity for both the memory as well as latency. So these are the references. Before ending this, I just wanted to show the visualization of the axial positional encodings. Yeah, so I'll just explain this. So here you can see the 49 by 4 random normal vectors. So this one. So here you can see the shape of the token matrix or embedding matrix. Once you do the axial positional embeddings like encodings, this 49 by 4 is being factorized into 7 by 1 and 7 by 3. So here you can see the values at the bottom. This is a 7 by 3 matrix, and this is a 7 by 1 matrix. So this 49 by 4 is being constructed using these two matrices. How you can see here, this 7 by 3 matrix can be seen here, this one. And 1.76 is this value, which is getting embedded to each of these 7 by 3 matrices. So that like you'll be able to reconstruct the 49 by 4 matrix just by using these two matrices. So if you can just visualize 49 by 4 means like approximately around 195 values that that you are supposed to store if you are using positional embeddings. But right now, since you are factorizing this 49 by 4 into 7 by 1 and 7 by 3, you can see how much 7 by 3 is 21 plus 7, 28. So instead of 195 values, you are just storing 28 values. So as and when the sequence length and embedding dimensions increase, you can see how the there is a significant decrease in the memory or the size of the matrices. Yeah, that's it from my side.